Hello again, I'm Stephen Bashong, Assistant Editor at Solar Power World magazine, and I'd like to welcome you to today's webinar, Solar Racking Reliability, Will Your System Stand the Test of Time? I'd like to take just a moment to thank today's webinar sponsor, the Aluminum Extruders Council. Before we begin, I just want to go over a few house cleaning items with you. This webinar will be available after the presentation on solarpowerworldonline.com and also will be emailed to all registrants. Secondly, there will be a question and answer session at the end of all the presentations. We encourage you to participate. You may submit your questions at any time throughout the webinar by typing them into the GoToMeeting panel on your right. Lastly, we realize not everyone who would have liked to attend this webinar could, so we encourage everyone to tweet about key topics and discuss takeaways using the Twitter hashtag #SolarWebinar. So at this time, I'd like to introduce our presenters. Today we have Brian Wild, who is the founder and chief technical officer at Equilibrium Solar, and Yuri Reznikov, vice president of products and strategy at Sunlink. We're thrilled to have you both here today. Brian will begin our presentation today. A little bit about Brian. Brian Wild is the founder and chief technical officer of Equilibrium Solar. He possesses a strong background in the solar industry, plastics, engineering design, and product launches. Brian holds a master's degree in mechanical engineering from Georgia Tech. He also achieved a photovoltaic installer certification from the North American Board of Certified Energy Practitioners. Previous experience includes working for General Motors as a design engineer in the plastic parts division, for Sundance Products as Director of Engineering, and for a fast-growing solar installation company as Applications Engineer. Brian has managed $1 million in construction projects, been involved in several GM product launches, and has prior entrepreneurial experience. Brian, we're so happy you could spend some time with us today, so please go ahead whenever you're ready.
Okay, appreciate the introduction. As you mentioned, I've got some experience in polymers with General Motors and other companies. Before I begin, I'd like to thank everybody for their time today and interest in this topic, not only reliability, but what it means with respect to polymers, a topic near and dear to my heart. I'd like to say that my experience is in applications engineering with respect to polymers, not chemical engineering. So I guess you could say I understand how to match polymers with the appropriate applications more than the molecular structure of polymers. So it's more, what a polymer can do, not why it does what it does. So that's my perspective, and I'm bringing that to the solar industry. And of course, before we dig into polymers with respect to longevity, there's a lot more to be considered when designing a racking system. Some things listed here, hopefully it'll be touched on in the next presentation in Q&A, but I'm going to use the short time I have to talk about polymers, and that's the weatherability bullet point here. Of course, weatherability for metals might be corrosion and other things, but I'll talk about what weatherability means with respect to polymers. Of course, why the topic? We all know that the use of polymers in solar is growing fast, but polymers is relatively new to solar industry. And what that means is that maybe we don't have the experience within solar, and we have to draw on experience in other industries to understand will polymers last. So here's some reasons, that we're bringing polymers into solar. Of course, you can design, snap features and things you can't do with other processes. Of course, polymers don't corrode. With respect to flat roofs, it's nice that we don't have sharp corners or burrs to worry about that could rip a membrane. Lightweight, of course, low cost is the driving force behind why polymers are coming into solar. But we have to be careful to make sure that we're not just lowering the cost and sacrificing quality. And so I'm hoping to give you some tools and maybe more consciousness on the type of questions we should be asking to answer the question of will they last. I've highlighted 4 properties here that are important when we talk about polymer longevity in solar. Of course, there's 100 properties with any given polymer and dozens of application requirements. Polymers can meet, all application requirements usually without a problem. And I'm not going to talk about the easy to meet criteria, but instead the hardest 4. These are the 4 that, if we're not careful, could lead to failures. So I want to zero in on the top 4 properties here. The first one is impact strength. Impact, as opposed to strength itself, is a sudden impact, whether it's kicking the part or hail hitting the part, or an actual event that happens, which could crack a polymer. There are various tests to measure the impact strength. That falling dart, notched izod, multi-axial, Sharpie. Those are 4 common tests that we can use to very easily measure impact. So we want to make sure that, of course, out of the gate and in the future, these parts don't crack. There's also real-world testing and hail testing specified by UL 1703 that you can ask for product-level validation. UV resistance. Again, UV resistance is probably the primary topic, with respect to polymers and longevity. And so this is the one that we really want to zero in on to make sure that not only the impact strength and performance and color are good out of the gate, but they're also good for 25 years. We can measure UV resistance various ways. There's various types of accelerated weatherometers, weathering chambers, such as xenon arc testing. And typically, you have 1,000 hours in the chamber equals 1 year of actual test. So it could still take a year or 2 to get to 25 years, maybe more. Depends on how fast you accelerate. But there's also there's plaques that whether it's in Florida or Arizona, Florida typically being the worst case because you have a combination of high temperature plus moisture plus the high UV. And so those 3 together, usually we send plaques to Florida, and plaques are just square, flat pieces of the material exposed to the sun in a lab climate so that we can check properties at various lengths of time of real exposure. So and then there's real-world testing, which is take a part out of the field 25 years later and test it. So those are 3 ways we can test for UV. I'll have a slide later that digs into UV a little bit more. Fire resistance is the 3rd property I want to talk about. Of course, it's coming up in consciousness with 2703 requiring it, California standards, and of course we want to make sure that we're not adding fuel to the fire. UL 94 tests the polymer itself, and there's a part level test within 2703 that's very similar to how they measure the flame resistance of roofing materials. So in 2703 you have a fully assembled racking plus modules, and they can test whether or not the polymers meet 2703. So that's how we test for fire. The 4th one is temperature resistance. I think this one often goes under the radar. Temperature resistance is basically maintaining strength, stiffness, shape at elevated temperatures. We all know in solar you can get 160 to even 190 degrees Fahrenheit in the field. We want to make sure that there's no creep or warping that happens with polymers. So we can test this property very easily in the lab. There's a couple ways to test it. Heat deflection temperature is, I think, a key way to test it because it not only heats the material, but it also holds a load onto a tensile bar. And if that bar deforms a certain percent, then it fails. So it's basically holding its strength under an elevated temperature. And the result of that heat deflection temperature, it gives you a temperature at which the polymer will not yield, the highest temperature that it will not yield. And of course, cost is you know, the reason for the increase in polymer use. So on the left-hand side of this chart, you'll see the 4 properties that I've highlighted and some others that are key properties for polymers within the solar application. ASA meets a lot of the requirements that are more black and white. Flammability, for example, is a yes, no, you either pass or fail. Recyclable is pretty black and white. It has not only to do with the ability to be recycled, but the market for recycled materials. So flammability in this chart, heat deflection temperature, impact resistance, and UV resistance are the 4 that I just mentioned. And you can see how they play out with 3 materials that are used in solar today. Not to say that there's not more materials that we could be using or that we will use, but these are the 3 that you typically see in solar today. I'll talk through each one. I mean, it's pretty self-explanatory. I mean, ASA meets a lot of the go, no-go tests for solar. It exceeds performance within UV resistance, which I think is key. So, you know, it has inherent weatherability that we'll talk about later. Polyethylene, primarily HDPE, you know, is what's used. It has some strengths and weaknesses above and beyond and below ASA. Certainly weaknesses here are, you know, flammability and heat deflection temperature are 2 that you want to keep your eye on when you're talking to potential vendors. And the last material is a kind of a high-end material. It certainly outperforms the first 2 materials on most categories. A very expensive material. Recyclability is questionable as far as it's so specialized as a material. It's hard to get a market for that. And it's a pretty heavy material too, or three drawbacks. So again, applications engineering is all about finding a material that meets all your criteria and then for the lowest cost. So that's why we chose ASA, we being Equilibrium Solar for the EcoFoot 2. While it is much more expensive than HDPE, it also has superior weatherability and meets all the other requirements. Just a little more information about ASA, since that material is not well known in solar, and even outside of solar, it's not one of your common commodity resins. You know, this graphic highlights some of the major selling points of ASA, and of course we're going to zero in on the weathering. Okay, so weatherability of ASA is different, you know, than weatherability of, you know, polymer B, C, and D. They all break down a little differently. So I'll just talk about ASA right now. Before I dig into that, in general, the weatherability of a polymer, what does happen? Why does it break down? Is the first question. So, in really broad terms, the sunlight is energy, and that energy attacks the molecular structure of a polymer and can break the chain. And with humidity there and other elements there, can break the chain permanently and form new bonds and slowly degrade that plastic. And what you see on a macro level happening is you don't necessarily lose strength. You might lose your color, and then your impact strength is really a key property. So if somebody tells you about, you know, whether, you know, UV resistance of a polymer, ask for a graph with respect to impact properties, since that's what goes. You know, your experience in a consumer life may have been like this. You have a garbage can, you can kick it and it doesn't break, you love it, and then a year or 2 later, you barely drop it and it cracks. You wonder what happened. Well, the shorter chains, the degradation, you know, leads to that cracking. So that's what we want to prevent. So specifically with respect to ASA, it was designed in the 1960s by BASF, specifically for outdoor applications. And the nice thing about ASA is it doesn't require any additional UV stabilizers, which sometimes have a limited lifespan. And instead, it's inherent in the ASA matrix that it kind of holds up to the UV. So again, impact strength is what we care about. That's what we measure. That's what we look at over time, because it's not that the trash can wouldn't hold a load. It's that it wouldn't handle an event. Okay. So again, the ASA has, for ASA, it's got a different kind of rubber which doesn't break down. You can also add UV stabilizers in addition to that, but that helps it last longer than some other polymers that rely on UV stabilizers. Before I go on, so the UV stabilizers aren't a good or bad thing necessarily. Let's see. So I don't want to dig too much into all the different stabilizers, but the categories of them are like this. You have carbon black, which is the cheapest stabilizer that might last 5 or 10 or maybe even 15 years, but it has a limited lifespan. Unfortunately, that's what a lot of people use only. And then the next level of defense is maybe like a Howells or a different, inherently a different type of UV stabilizer that has a much longer lifespan. And then you have to dig into, what exactly is that stabilizer. But before, instead of going into all the different stabilizers and which one lasts the longest, really what you want to know is results. Like, show me results. Show me that you use what somebody else has used that correlates to this graph, So that's a good way to approach the conversation with your racking suppliers. Here's just a graph with ASA. On the right, you'll see there's a break-in period, typical, similar to modules, like a break-in period, and it begins to level out. At some point, it could drop off if not well protected. That's kind of a typical curve of weatherability. I guess that brings us to the end of the presentation. Of course, the theme here is that, look beyond the warranty, even look beyond the bankability of the company, because we all know large or small companies can exit solar, and what will remain is the product on the roof. And so I think a lot of the focus is transitioned to, technical validation of the system and of the product, and less of the bankability and warranty, because that's harder to pin down. But if we know we've got data, it's going to last beyond 25 years, then it doesn't matter. The warranty doesn't matter. That's all I have prepared.
Thank you so much, Brian. That's a lot of great information there. We're going to move on now. We're going to hear from Yuri Reznikov from Sunlink. He's the Vice President of Products and Strategy there. First, just a little bit about him. Leveraging more than 15 years of experience in product management, strategy, and business development, Yuri leads a team that manages all aspects of the Sunlink product portfolio, including new product expansion, pricing strategies, product requirements, and roadmap development. Prior to Sunlink, Yuri spent several years working in the investment banking industry. He also enjoyed a notable career with Intel Corporation, where, as a product manager, he was responsible for desktop processor strategy, positioning, and business development in the computer gaming space. In addition, he was part of the Intel Leadership Development Program, where he spearheaded EMEA program expansion, drove business development with Intel Capital portfolio companies, and drove development of a peer-to-peer software product. So thanks again for being with us here today, Yuri. Please take it away when you're ready.
Great, thanks, Stephen. And thank you, Brian, for that education on polymers. Thanks, everyone, for joining. I'd like to start off with just talking a little bit about Sunlink and who we are. We have more than 300 megawatts installed today, 2,000 plus sites, primarily rooftop. We have done a lot of the ground mount projects in the last 18 to 24 months as well, whether that's commercial and utility scale. But we are a mounting system provider, focusing on commercial utility scale markets on the mounting system, but also combiner boxes system, balancer system products as well. I wanted to talk a little bit about quality and reliability and how we see those aspects from a product perspective. When we think about quality and reliability, and I think as we think about this as an industry, we really need to focus on two main things. Number one, and most importantly, is life safety. With these systems out there in the field or on roofs for 20 plus years, life safety is ultimately the most important. And this is what the code tries to do, is we design systems according to code. It's really life safety that we're concerned about. And this is panels, flying off rooftops in all kinds of different events or other such things that nobody wants to think about and nobody wants to see. And then the second piece, and this is maybe a little less important, but nevertheless, if you're a developer or an integrator, the key thing to watch out for is maximum energy production. So even if there's a small environmental event, such as maybe Sandy or some other wind event or snow event or earthquake event, you want the system to make sure to maintain energy production, to limit those O&M requirements so that not everything moves out of shape. You don't get wires breaking and certain things happening with minor events, even though life safety is not an issue. So those are the two levels that I think we really need to look at as an industry to make sure that the systems that are out there are designed for, number one, life safety, and really, number two, maximum energy production or operational requirements. And I added the third bullet here because I don't think we can talk about the first two without really taking into account total lowest cost. And this includes the hardware cost, installation cost, and obviously the cost of performing O&M. Because it's not quality and reliability at any cost. We are in the solar industry, and as everybody knows, the third bullet there is quite important. So with that in mind, I mentioned things that can happen, and nobody wants to think about it or expecting things to happen. But when we think about systems up there for 25 years or so, we do have snowstorms that put tremendous load on the system. We do have seismic events that put tremendous load on the system, and obviously we have things like hurricanes and storms and tornadoes, etc. And although most systems are up there without any issues and they've been designed to code, that we have seen as an industry certain failures. There's been failures with modules basically either on rooftops, turning over, doing some damage, not only to the production piece, but frankly, some life safety concerns there as well. And so it's quality and reliability, but really in the sense of life safety and production. So with that in mind, I'll talk a little bit about today at a fairly high level on things that I think we as an industry need to be conscious of. And so the developers, integrators, and folks making purchasing decisions from a mounting system perspective really need to look at these things. And those are wind tunnel testing, make sure that that's done in the right way. Same thing with seismic analysis. Not only would you have the right data and you're doing it at the right testing facility, but once you have that data, how do you actually apply it to individual projects and what does that mean? Once you have that data, taking a look at product design and mechanical testing. The theme that I'll talk a little bit about today is not only theoretical data gathering, data analysis, but absolute validation from a physical testing perspective. Supply chain, this is something that I think maybe goes a little bit under the radar, but if we're not doing our things right on the product, on the supply chain side, anything that we do on the product design or wind tunnel testing or anything like that gets thrown out the window if we don't have good relationships and proper standards with our suppliers, whether that's internal or external, and construction practices. Same type of philosophy. We can do everything right, and if we don't manage our customer and the installation crews out there, one little mistake, not torquing the bolts properly or not following the installation instructions properly can really put everything to risk. And so that's what I'll try to do today, talk a little bit about each one of those areas.
Hey, Brian, excuse me. Interrupt you for just a moment. I have a commenter who says it's a little bit difficult to hear you, so if you can speak up at all, that would be great. Thank you.
Stephen, I appreciate that. I will try to do that. And let me know if you still can't hear me as I continue.
Thank you so much.
So we'll talk a little bit about wind tunnel testing. Briefly, there's all kinds of wind tunnel testing out there in the industry, and everybody does it because that's really the way to design cost-effective systems. You know, the requirements there from a wind tunnel perspective are mainly threefold. Number one, it has to be in a boundary layer wind tunnel. So what that means is that we're not talking about an aerodynamic tunnel where airplanes are being tested or even cars are being tested, but really we want to measure the flow of wind over certain objects, because these arrays are put in an area where we do have other buildings in the way, trees, etc., which create fluctuations in the wind, vortices, etc., that control the air over these panels. And you can see in the picture little blocks within the wind tunnel, and that's supposed to simulate some of these vortices and direct the flow of wind over that array. And that's critical. Number two is the code was really designed to test a specific building within that project. So they're originally designed to test skyscrapers. So you would design a building, you would put in the wind tunnel, and you would model the airflow around that building and what the loads are on that particular building. In the solar industry, we can't do that. There's a lot of different projects, there's a lot of different types of buildings, and we really need to be able to generalize that. And then last is we're not talking about full-size scale models. This is not putting a fan somewhere with a full-size array. This is really about making sure that your model is small enough to get the actual aerodynamics and the flow of air over that system to simulate real-world conditions, but at the same time having enough granularity in that model to make sure you're capturing the right amount of data. And that's basically what it means when you're trying to design systems to, as you can see in these pictures, that are very, very unique. So some of the buildings are going to be oval, some of the arrays are going to have very unique shapes. The goal is to really have enough data and to test enough variation to be able to generalize from that data what the effect on that system would look like. And that's really what I think I'll use Sunlink as an example here. What we've done is run over 1,000 tests, 75 building array models, and these are some of the variations that we've run to be able to gather this data. Not only tilt angle, but height off the roof, spacing between rows, setbacks, deflectors, different roof heights, and then all kinds of combination of these factors to basically end up with about 30 million plus pressure readings for each of the 1,000 test runs. That is an enormous amount of data, and we think that from an industry perspective, you really have to have this much data in order to really understand what an array will look like on a particular building with a particular layout and how the wind is going to affect that. So from that perspective, I would urge folks to ask those types of questions. Say, well, how is the testing really done? How is the data gathered? And what does that really mean? I'll give a little bit of insight, and this is a video, so bear with me. I'm going to try to turn it on, and I'm not sure if this is going to work. And I don't think it will. But suffice it to say that this was showing the, well, maybe it will work. This was showing the wind flow within that array. And you can see a very simple array. You can see net uplift, underside, upper side. It is playing, if folks can follow that. The wind is actually coming from the northwest direction. And it allows to show you the variation on what those pressures look like on a particular array. And you can see when you're modeling that, just that simple shape, what the uplift is, what happens on the under the array, what happens on the upper side of the module, and where the ballast or the connectors need to be placed to make sure that that piece is held down. And it's really created by vortices, whether that's a corner of the building, whether that's some sort of a tree or some other objects within around the building. That's what really creates these fluctuations within that array. And this is a pretty simple example. So when I look at the next slide, and I talk about how do you put that data and how do you model that data on a particular array that looks something like this, where you have all kinds of corners and a space in the middle. And you can see that when we're applying data to that particular array, we're actually creating a SAP model. We're using pretty sophisticated computational models to try to predict what kind of situations this array will face, what wind from every different direction, and where we're going to see problems from an uplift perspective. And those are the areas that we try to ballast, or we try to put connectors on to make sure that that doesn't in fact happen in a real life situation. We do something very similar with seismic. This is another video, and I'll try to play it. And this is a model that we've created using historical data and using the array data that we have from that particular project to try to understand, when we're creating fully ballasted systems in a seismic environment, what that system will react to, what that would look like, how that model is built, etc. And if we ballast that array in certain areas, what is the effect going to be in a particular seismic zone with particular cases? And we've actually not only tested that from a model perspective, we actually went in and we looked at, we used a multi-directional kind of shade table at UC Berkeley to test a full-scale model to try to validate our theoretical model to see, hey, are we doing things right? Just because our model and our calculations say that this is what the behavior that we can expect, that doesn't mean that we can't tweak it, doesn't mean that it's actually going to perform in the same way in real life. So we've actually done that. We've put this array on different roofing surfaces. We've put this array on wet and dry conditions. We've tested it, and we went back and closed the loop on our theoretical model to make sure that we have the right data to design these projects. And what we're doing now is we're trying to work with the industry, open up this data to different industry groups, and publish this data so we can get the industry on the same page with respect to wind tunnel testing or seismic testing. And if you look at the CEOC, some of the papers that come out of there, this is the Structural Engineering Association of California. They're using some of this data to publish some of their reports on the proper way to engineer solar systems. Let's talk a little bit about product design and mechanical testing. You know, I wanted to position this presentation as kind of going in order of, first we need to get the data, then we need to apply the data. Then now that we know the loads on some of these arrays and some of these systems, we have to make sure that we're designing products that actually fit those loads and make sure that they can handle those loads. I think Brian did an excellent job talking about the polymer-based systems and what type of things we have to watch out for when we're designing systems with that type of material. I think the same thing is true when you're designing with steel and aluminum, and what the thickness is and what the type of steel, and is it galvanized or not galvanized, and all those considerations have to take place depending on what the loads are that we've gathered from our wind tunnel and are applying to different environmental conditions within that project. And we're doing this primarily by calculation. So not only are we looking at yields and torsion and strength of all these different components under different loads, we're also looking at field assembly, O&M considerations. What is the corrosion going to look like? What about grounding? How is the system going to be grounded, and is that going to create a long-term issue down the road with respect to quality and on the reliability side as well? And so what does that mean when we talk about calculations? Well, again, when I talked a little bit about closing that loop, we have to make sure that we do the testing to validate some of those concerns and some of those calculations that we have. Again, it's from two different perspectives. It's from the perspective of life safety, and it's from the perspective of operating performance. Just because this piece, some sort of a rail, buckles under a certain load, that's going to create a life safety issue. We want to make sure that that doesn't impede the operating performance. How do we design that particular component to make sure that whatever system's on the roof, it continues to perform as designed under various conditions without a significant amount of O&M or replacement components for the life of the system? So not only are we testing the overall system, we're testing individual components, we're testing the prototypes that we have, the machine components. We also need to test the tool parts coming out of the manufacturing process. Just because we have a prototype that tests well, we have to make sure that the stuff coming out of the assembly line, the stuff that's actually going into the field, performs just as well as the pieces that we've tested. And I give a couple of examples here: coefficient of friction, yield curve, strength, etc. But it really is important to make sure that not only the calculations are done, and if we're doing some sort of SolidWorks calculations or simulation, we validate that data with physical testing. Supply chain. I talked a little bit supply chain in the introduction, but this is another one of those pieces that we really, as an industry, need to make sure that there's clear standards. And this is not anything new to the solar industry. This has been done for hundreds of years in various industries. But I think in the solar industry, this has got this is a little bit under the radar. And I would encourage folks making decisions, looking at mounting systems, really do a lot of the due diligence on the supply chain, because no matter how we design our mounting system, how we test them, what documentation we provide, if we don't have a supply chain or manufacturing process dialed in, we're not going to get the results that we expect. And so from our perspective, we use a Six Sigma methodology: define, measure, analyze, improve, and control. We work with our suppliers to make sure that they have corrective action reports. If there's a mistake, we follow up. We have a process in place to make sure that we have quality products coming out of that particular partner. And whether that's an internal process, an internal supplier, meaning the manufacturing is done internally, or the manufacturing is done through contract manufacturers in the US or even internationally, these type of processes are absolutely critical to make sure that we're getting quality components. And when we think quality, we think right quantity, right product, and delivered at the right time to the project site. We do this with periodic inspections, and as I mentioned again, we do the physical testing. It's not just enough to have the documentation and to have the relationship. Every piece that comes off that assembly line, every new piece that's been designed and tested, whether it's first article inspections, go through a pretty rigorous testing process to make sure that what gets delivered to the site is absolutely the right that was meant to be there from a design perspective and from a manufacturing perspective. And then the last piece I'll talk about is construction practices. Because this, again, if we're not managing this process with our customers, then I think we've lost something. And this really, there's a lot of pieces that the construction crews have at their disposal to do things the right way or potentially the wrong way. So when we think about ballast configurations, where that ballast goes, same thing with connectors. What about roof layout and field changes? If there's an air conditioning unit discovered on site that we didn't think was there, well, how does that affect not only the structural requirements from a wind perspective, but also what about that requirements from a ballast perspective and the loads and the different components that we have in the field? How does that loop get closed? And I put torque values here, just another example of a very simple thing that if we're not managing correctly, if the product is designed with certain torque values, not meeting those torque values in the field, well then from a quality and reliability perspective, we're not really getting the product to withstand the 20, 25-year life as it was designed to be. So a couple of suggestions for folks really looking to make sure that the quality is there from a construction perspective. Make sure that there is a comprehensive installation manual. The more details, the better. Make sure every detail is really spelled out from an organized process perspective. Installation methodology. This is critical. If the mounting system company has not thought out their methodology of how to install the system in an intuitive way, you're going to see construction crews basically take that into their own hands, put their own processes in place that may or may not get the product in the shape that it was supposed to be there. Another way to accomplish that is training videos. Warehouse training with construction crews. Make sure that the customer comes to the mounting system, does the dry run, gets the education tours, builds a 10 kW system or whatever it may be. Make sure that they're familiar with how that thing goes together. And then most important of all is you have to make sure that the mounting system company comes out to on-site, make sure it solves all the issues, answers any question from the construction perspective to make sure that there's only the pieces that have to be there are assembled in the proper way and are there. And we absolutely need to make sure that that's done. And that's basically my summary. I did this at a pretty high level. I still think it's absolutely critical to make sure that as an industry, from a mounting system perspective, we're doing things the right way from a wind tunnel testing and seismic analysis perspective. Not only are we getting that data, but we're applying that data in the proper way. We're designing the systems with the lifespan in mind. We're doing the testing. We're closing the loop on all these different pieces to make sure that we validate our assumptions, validate our calculations. We have the right processes from a supply chain perspective, and we're absolutely managing the construction practices. And that's it.
Thank you so much, Yuri, for your information there. I'm sure now that our audience has quite a few questions. I have some coming in already. So we'll begin asking those. Just as a reminder, however, you can submit questions at the GoToMeeting panel on your right. Also, if you would like to speak to one of our presenters or myself, the contact information is right there on the screen, so you could ask them a question directly. I'm going to begin. There's a new fire code coming out, and somebody asked how fire testing requirements come into play for both of these systems.
So this is Yuri, and I can take that initially. So that's absolutely right, and I didn't mention that, but it's absolutely true. There is new fire code standards coming out. This is becoming a very, very important issue in the solar industry to make sure from two perspectives that we have the right systems in place from a fire propagation perspective, meaning if there's a fire inside the building that the system doesn't amplify that concern. We need to have the right materials in place, and the materials are put together in such a way, and the system is really designed in such a way that it's not propagating the fire and increasing that risk. So when I talked a little bit about life safety or operating performance, this is really one of the things that can absolutely allude to that. We don't want the system endangering and making things worse from a fire perspective. This will be a requirement that most mounting manufacturers will have to, or all mounting manufacturers will have to comply with. We already are seeing a lot of the jurisdictions basically ask for that testing, and I know a lot of folks are in the process of getting certified to that standard. I expect a lot of the designs will have to be changed, and a lot of the materials that folks use will have to be changed. But this is absolutely a critical piece for us to move forward in the future to make sure that we have life safety in mind when we move forward as an industry.
Brian, how are you? Go ahead.
From a polymer perspective, it's very important. We're keeping our eyes on this, as it evolves, and of course reacting to it, which means that the materials may have to be changed. In the polymer world, what it means is that you can take a base polymer, add a FR package, a flame resistance package to that polymer. Adds a little cost, it changes the properties a little bit, but generally it's the same polymer. And the package that you use has orders of magnitude as far as how resistant it is, and they can be measured by the UL94 as far as what classification that polymer is in. And so really we just need to make sure that the packages we use meet the code requirements, kind of as they evolve.
Great, thank you. I did not set this webinar up to be a polymer versus metal discussion, but someone asked the question regarding one of your slides, Brian. He just wants to know more about how polymers compare to metal systems. I know they're relatively new, so I think it's a fair question to ask.
Yeah, I mean, with respect to what property, or we can answer it a lot of different ways. I kind of outlined, the reason that polymers are becoming more popular, not only with cost, but also, lightweight and corrosion resistance. And I think as long as we do a good job with specifying the right polymers, it can last 25 years. Then polymers have their place. Of course, it's not in applications engineering. There's no general right answer. It's looking at that individual part, its performance requirements, the best material to meet that requirement. And that might not just be polymer, it could be any material. So we do the same thing at Equilibrium. Not everything we use is polymers. Sometimes it makes more sense to use aluminum or galvanized, etc. So really it's a matter of applications engineering, picking the right material for the right product design. It's not a black or white question. You look on your automobile, there's a lot of polymers, there's a lot of metals. They can work well together. It's choosing the right material for the right application.
Great, thank you. A question for Yuri. Does Sunlink consider SEA OC guidelines and analysis of data collected with wind tunnel testing? If so, can you elaborate on how you adapt product layouts, et cetera, to meet the criteria?
That's a good question, and to be fair, I'm going to have to take that one offline. Please send me that question, and I will get back to you with an answer.
Very good. Here's a question for both of you. Is it a requirement to run simulations on the wind side for every system?
So I can take that initially. So at Sunlink, we absolutely do that because of the way that we design our systems, of the way that we choose to have our methodology in place. Right now, our systems are designed in such a way that we're using load sharing as a technique. So if we see a gust of wind in some corner, that load gets propagated throughout the array and it gets diminished. So we have various members cross-bracing the system north, south, and east, west. And we feel to truly optimize that methodology, we have to run the simulations to make sure that we're not being overly conservative and we can dial in the exact number of ballasts that can be done. I believe most other folks are using more of a spreadsheet approach, which means that you would divide the roof zone into various areas, and you say, for this zone, you would put, and these environmental conditions, you would put X number of pavers, and for this zone, it would be Y number of pavers. We believe that we can get better results using our proprietary simulation methodology. That does require lots of software, lots of space to be able to scale, but we think we can better optimize the system for the various environmental conditions using that type of methodology. But to answer your question, I don't think that that's absolutely a requirement.
I can chime in on this as well. Thanks, Yuri. This is Brian. At Equilibrium, we rely heavily on our partner, RWDI. So I think it's worth noting that not all wind tunnel firms are the same. Even if you have a wind tunnel, it's not only the wind tunnel, but it's also the access to historical data and the ability to generalize data. So, CPP, RWDI, there's a couple others that are known in the solar space to have a big database of data. And for us, it's not just data with our system, but it's also data that generalize all the different variables and how they play together. So we kind of draw into their data and their methodology to design a system, a balanced layout, if you will, for every specific project. So long story short is each wind tunnel firm, each company has their own little methodology process. They're all a little bit different. As long as you're partnering with those that have a lot of experience in solar, that's really the main criteria.
Great, thank you, Brian. A question for both of you again. What recommendations do you make for installations of your systems on a single-ply membrane like TPO, PVC, or EPDM roofs to provide for the best roof life?
I could take a shot at that one. I mean, the very first thing you do is check with your roofing manufacturer, and they have their own manuals, white papers, approval processes to determine all the things you need to have in place to make it, quote, solar ready. Following that is really the first step. So a lot of them do require slip sheets, they require certain mill thickness, and they require other things we won't get into, but just make sure that you're not only reading that, complying with it, but also obtaining, as an installer, obtaining, a warranty extension for your solar system. So that often means a pre and post inspection by the roofing manufacturer to make sure your warranty is maintained.
Yeah, and I would just add that that's absolutely true. I mean, the roofing manufacturer really needs to be kind of the final opinion there on what's appropriate to maintain their roofing warranty to make sure that you're in compliance there. I will say that you probably don't want metal touching the roof directly, even if you're using slip sheets. You want some sort of an interface there, whether it's Brian's polymer-based system or we use kind of a rubber compound to create feed, whether it's recycled rubber or rubber extrusion, to make sure that there is a friendly compound touching the roof, whether or not you install slip sheets, or if slip sheets are required, I should say.
Good point.
Thank you. For installations near salt water, a person asks, for installations near salt water, I can imagine the advantages of polymers, but what metals are okay to use? Is this an issue? When? How close to water can you use these systems? Yuri?
Yeah, that's a good question, and it's not a quick answer. So the short answer is probably, look, aluminum is going to work better from a corrosion perspective than steel, even galvanized steel. Having said that, there's different ways to attack that problem because, again, if we're concerned with life safety, we're really concerned with that corrosion from either a grounding perspective, so where you have corrosion, so where it creates faults in the system, that creates a problem, or the corrosion basically wears down the structural members where they can't handle the load anymore. And you can deal with those two things in different ways. Number one is using aluminum, and depending on the conditions, that may be good enough. Number two, you may want to just upsize your steel members so that even with the wear for a 25-year life, you still have enough structural capacity there to withstand that corrosion. Or the third option is maybe you want to put extra layers of galvanization on that. So your typical steel components are G90. Well, maybe you want to put a couple of different layers on there, extra layers on there, so maybe it's G180 or something like that, or use a special coating, some marine type coating to make sure that those steel members withstand that. But the short answer, and what we typically see, is folks just go to aluminum-based systems in locations such as Hawaii or Puerto Rico or some of those locations on the water.
Very good. Thank you, Yuri. A question for Brian. How will UL 703 affect polymers?
Well, there's the UL 2703 as written today, and there's the one that will be finalized in the future. I can talk to the one today a little bit better, since some elements, specifically the flammability and specifically the Class A side of flammability, still a little bit in the air. How does it affect polymers? Well, it does, with respect to flammability, raise the bar, and that means that the HDPE type products will need alternative materials. So it definitely will change the materials that are used. It's possible to get a flame retardant HDPE. I'm not sure if that's the way the industry will go. It might just be an alternative material altogether, which is more inherently flame resistant. So that's one property that's going to change polymers. Of course, heat deflection, temperature, structure, and it all just kind of make sure that the design and materials that were chosen do perform. So I think it does keep everybody honest and on the same page. So I welcome that change.
Thank you. Question about warranties. Just how important are they in your purchasing decision if you're a developer? For both of you.
Yeah, so this is Yuri, and I think Brian alluded to this a little bit, that warranties are important, and I think it's a signal to how the company chooses to stand behind their products, but nevertheless, again, as Brian pointed out, in the solar industry, the companies don't necessarily, you can't expect companies to be there for 20, 25 years in this space, and so it really, I think, is up to the customer to really do a little bit more due diligence on the product itself to make sure that you don't have a warranty claim if you can avoid it at all. Make sure that you do the proper investigation of the product itself to make sure that the warranty issue is not a kind of a backup option, but it's an extreme case option. And so I would definitely say from a warranty perspective, it's nice to have, but it's not the end-all be-all.
Very good. Brian, did you have anything to add, or?
No, I just concur. Definitely focus more on the technical side of things. If you do want to put some weight on the warranty, of course, you know, you got to look at maybe third-party backers or larger companies stand in front of the warranties that are out there. So, yeah, warranties can vary quite a bit, can mean different things. In the end, if you have done all your engineering right and validation, we'll never have a claim, and that's the goal.
Great. Well, it's nearing the top of the hour, which means we are out of time. So I'd like to thank Brian and Yuri for their participation today and sharing all of this great information with us. And I'd also like to thank the Aluminum Extruders Council for sponsoring this great webinar. Also, thank you to everyone who tuned in and listened today. I hope you enjoyed the presentations. Please join us for future Solar Power World webinars. There's a lot more to come. Thanks, everyone. Take care.